Hey, I wanted to work some problems from the second law today because that's kind of where we're going. So let me just put some of these up here. I wanted to remind you that the second law says F equals ma, and anytime we have more than one force, we need to draw that box and draw a picture of a box and put the forces on it that act on it, and then we kind of put a sigma here to say add up all the forces. Set that equal to the mass times the acceleration. Okay, so that's what we're going to do over and over here, just for some practice with this. Now, one more time with the free body diagram, in order to add the forces, you have to be able to see what the forces are. So when you read a problem like this right here, and it starts off and it says gravity pulls down on a 4 kilogram box, that mass right there makes me think, oh, I got some weight going on. Don't know if I need it right yet or not, but there's a downward pull right there. Gravity is pulling down. You could either write gravity on that, or like we saw last time, it might just make more sense to just put mg and say, well, that's the weight of the box, the force of gravity pulling down due to gravity. All right, I'd probably just put mg on it, be done with it. Next up, it says it's held up by the floor. Okay, so if I've got floor here, I know the floor is pushing upwards on that, supporting it. And remember how we called that the normal force? Okay, and as it was, those two canceled out, and we didn't usually have to do anything with that. So you can decide whether you want to put them on a regular basis or not. If there's any other vertical forces, if somebody's pulling up on the box or pushing down on the box, then you probably do need to put those on your picture and to think about what's happening in the y direction. All right. Over here it says a guy pushes to the right. That's a force that needs to go on my picture. Force. Okay. You could call it F sub g, the force of the guy, but that's going to sound like gravity. Whatever you want to call it is fine, but you need to understand that there's a force pointing to the right. Friction acts to the left. We haven't talked about friction yet. I got a whole video coming up on that one. But F sub F is the normal abbreviation for that, so I just put F sub F right there and be done. Trying to swoop in from above. There you go. F sub F would be a good way to mark that. Do you see how I draw a box and I draw all the forces? We don't even really want to do anything with this one here, but that's the heart and soul of this thing. And as soon as I have my free body diagram drawn up, then I can say the sum of the forces in the x direction equal mass times acceleration, and the sum of the forces in the y direction equal mass times acceleration. It's a two-dimensional problem, stuff going on up and down. I consider that over here. Stuff going on left to right, it's right here, okay? And I could say, well, in the x direction, I got this guy, F. It's to the right, let's call it positive. I've got the friction. That's acting to the left, so negative, positive to the right, negative to the left. It's equal to mass times acceleration. Right here it says this one's constant velocity. When I have constant velocity, my acceleration is 0. All right, so that would actually drop out, and I'd have that. And the force to the right perfectly equals, in magnitude but opposite direction, the friction. Okay, and so those cancel out. I'm pushing to the right, but just enough to overcome friction and keep it moving at the same speed at constant velocity. In the y direction, I got the normal force up. I got mg down. The acceleration in the y direction is 0. It's not rising. It's not sinking. It's not changing its speed up or down. So the normal force would be equal to the weight. Okay, sometimes that happens. All right, watch for that word constant velocity. That's kind of a code word there to say acceleration equals 0. All right, but I draw the box, I draw the arrows, I build the equations, I solve for whatever I don't know. It's always the same pattern. I don't know what that is. Looks like I copy-pasted the thing and it got stuck in there twice. Okay. A 30-kilogram girl in a swing is pushed to one side. You see, it's already talking about forces. Somebody's pushing on this thing. It's held to rest by a horizontal force F, so that the swing, that's supposed to be on top of the thing. I guess I copy-pasted and then it moved it down. Didn't know what to do with it. Let's put that up there and get rid of this one. I'm thinking about a girl. You could get fancy and draw a girl with arms and ponytails and all that. Here's the easiest thing to draw. All right, I need an object. I don't care what it is. It's a rock, it's a book, it's a something, it's a girl on a swing, but it's an object. So draw yourself an object. A box works really nice. Somebody is pushing her horizontal to one side. That's a force that acts like this. Okay, I'm going to call that F, like that. So that's the horizontal force to the, they call it F2, so that's good. The rope used to hang straight up and down, but now that I've pushed her to the right, the rope's kind of coming that way. And we need to give that a name. Tension works, the tension in the rope. So I could come in here, put an arrowhead on that, call it T. All right. And you might think, well, that's all the forces. I'm pushing to the right, and the rope is holding her up and canceling out my pushing to the right. But really, there's one more force here. Of course, gravity's doing its thing, so we need to put in the gravity. Like that. All right, I'll just put mg for the weight of the girl. Gravity pulls down. I push to the right. The rope pulls back up at an angle, 30-degree angle, respect to the vertical. We're coming in here, and there's the vertical. This is a 30-degree angle right there. Okay? But now we have that right there. So, we have a free body diagram with forces on it. Some of them are pulling up or down, some of them are pulling left or right. I need to break it apart into the X direction and the Y direction. But every time you see one of these problems, draw yourself a picture. Write down the sum of the forces equals mass times acceleration. If you're breaking apart into X and Y, put the subscripts. And then I need a list of all the forces that are acting left and right, and I'll add those up. Let's get those first right here. I think you can see that T is pulling up and to the left. I've got a little X component of T right there. That would be opposite the 30-degree angle. So I'd have to say T sine 30 degrees to get that piece. And similarly, down here, F, it's not going to let me draw it right on top. Oh, this might even be better. I'm going to change that to red. Ha! Okay. Those two red forces act in the X direction, so that's what I need to put in my X direction equation here. F pulls to the right, we'll call that positive. I'm thinking about a coordinate system for the X direction that looks like this. And anything to the right gets a plus sign, so that would be F. Anything to the left gets that. And that would be equal to the mass times the acceleration in the X direction, just copying the right-hand side here. We're just holding her here. They're held at rest. Nothing is moving here, so the acceleration is 0. And I'm not sure where this is going yet. I don't know F, and I don't know T, so there's two unknowns in that. I'm not really sure what I'm going to have to do. Why don't we write F equals T sine 30. We'll add this term to both sides, bring it over, and I can't solve that equation because there's two unknowns, but I can park it right there for a second. Let's go see what's happening the other way. When I think about the Y direction, I've got the tension. Oh, look what I did. Okay. Yeah, here we go. I got the y component of the tension. Tension pulls up. That's right next to the 30-degree angle, adjacent to it. So T sub y is equal to T times the cosine of 30 degrees. And that would have to go into my equation over here in the y direction. Also down here I have the weight is in the y direction. So I want to let's change that to a green arrow just so we can kind of see what we've got. In the y direction, some stuff pulls up, some stuff pulls down. Make yourself a coordinate system. Call one direction positive, I don't care which one, but the other one better be negative. And I'll come in here and write two forces, two green arrows. T cosine 30 degrees minus mg. Again, it's at rest. She's not moving, so it looks like that. And I could get everything on one side. Let's add mg to both sides. I know the mass. I know g. I know the cosine of 30 degrees. The only thing I don't know here is t. I could solve this one for t. T is going to be equal to mg divided by the cosine of 30 degrees. And again, I have all those numbers. There's 30 kilograms times 9.8 meter per second squared divided by the cosine of 30 degrees. That's going to be equal to t. And then see how I could bring that over here and put it in on this side. So this will work out fine. I'm going to get my calculator out. First thing I'm going to do is turn it on, but the second is to hit the mode button. Make sure that I'm set in degrees, because otherwise I'm about to goof myself up. All right, but I need to do 30 times 9.8 divided by cosine 30, and that would be 339 and a half or something newtons. Okay, and you can see the newtons pop up right there. Kilogram meter per second squared makes a newton. This has no units, so we're good. We've got the tension in the rope. That's one of the things that they wanted us to find. All right, and as soon as I have that number, then I can bring that up here and plug it in. It'll draw a line long enough for me in for that, and then it's child's play to kind of come along and say F equals 339.5 newtons times the sine of 30 degrees, and we'll see what that is super quick here. 339, I already got the number. I can go times sine 30, and that's 169.7. Okay, newtons. All right, so a couple takeaways here. You got to draw the picture. If you don't draw the picture, you will never get these right. You have to be able to see what the forces are, which direction they point, how many there are. If you can't see that, then there's no way to come over here and say, well, I've only got two forces in the x direction and two forces in the y direction. All right, so draw the stinking picture. Draw a box, the simplest possible picture you can. Draw a box, draw the three forces. We had the blue arrow, the red arrow, and the green arrow, and then we had to take some of them apart and get the components and everything. So there's some serious, thought that has to go into this, but the picture makes it pretty obvious what to do with it. The second takeaway here for me is that once I've got that picture, I am always going to write this down. Okay, that is the starting point for every problem on this test. We are doing Newton's law. Okay, and it's all going to come back to that somewhere. I don't know how I'm going to have to solve it. I don't know what I'm looking for. You're just kind of feeling your way through the dark here. When we did this one, for example, we said, whoa, I've got two unknowns. I can't solve that. What else can I do? Well, I can build the other equation. Look at that. I got one answer. That'll help me get the second answer. All right, so you just kind of It's like crossing a creek, you know. You kind of jump from one stone to the next, trying to keep your feet wet, trying to get to the other side. And it takes a little bit of experience and practice doing that. But there's nothing hard about what we're doing here. If you can draw the picture, you can build the equation. And if you can build the equation, you can solve the equation. All right, so it'll work out fine. Here's one right here. I've got a dolphin. It was going at one speed. It slows down. So here's my dolphin. That's not too bad, I guess. And it says that at the beginning he's moving 12 meters per second. You know what? I don't want to draw that. There's the dolphin, and 7.5 meters per second in 2.3 seconds. This is looking a lot like a kinematics problem, isn't it? Okay. What average force was exerted to slow the dolphin down? This is what I'm looking for, the force. Find the force. So I got to do something. I go, wait a minute now. Force, this is Newton's law. Old man Craig told me that everything came back to sum of the forces equals mass times acceleration. I don't have the force. Well, I do have the dolphin, the mass of the dolphin. That's good. But I don't have the acceleration. Could I get the acceleration? I've got V0, V, and T. That would work. I can get the acceleration because I know some kinematics. I know that V equals V0 plus AT. That's one of my formulas. And I could solve that for A. And when I put my numbers in, 7.5 meter per second, not squared, not squared, not squared, minus 12 meters per second, all divided by 2.3 seconds, that's going to be my acceleration. So now I've got a piece of the puzzle I didn't have before. And 7.5 minus 12, close up the numerator, and divide by 2.3 means I've got negative 1.96. Negative, why is it negative? Oh yeah, because I'm slowing down. Negative 1.96. All right, so that's a piece of the puzzle I didn't have before. I wonder if that's going to do me any good. Well, now that I've got the acceleration, I do have the mass and I do have the acceleration, so I should be able to multiply those and find the force. In fact, there's only one force here. I don't know what the dolphin does to slow down. Water resistance would be one explanation, but maybe he's got a way he wiggles or something to do that. If there's only one force and I'm looking for it, I could just go down to this and kind of forget about the sum of the forces. That force that the dolphin exerts, or that the water exerts on the dolphin, is this way. It's slowing him down like that. And when I come in and I put the numbers in, I've got a 35 kilogram dolphin that's decelerating 1.96 meters per second squared. You can see that's going to be a negative force. That's why it points to the left. Negative 68.5 newtons. Right there. Okay? I do have the force, and the negative says to the left, and a leftward force is not going to make him speed up. It's going to make him slow down. It's in the opposite direction. Coordinate system would look something like this. Direction of motion of the dolphin is positive, and that force and the accompanying acceleration are both in the opposite direction, negative. All right, so that's nice. Here's one. Got a potato in a potato gun. I don't know if you've ever built one of these, but they're pretty fun. Some good physics in that. You do need to be careful with it because potato gun can put a potato through a piece of plywood. So you need to have some room, have some respect for the thing, okay? But it's going to shoot this thing up, 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 up. It says the highest point up there is 110 meters. So that's interesting right there. That's way up in the sky. I'm thinking about this potato. We'll draw it. I don't know where I can draw it. Right there is the potato. And they give me the mass of the potato. Not sure how that's going to come into play yet, but let's put it down. I got an 80-degree angle. Theta equals 80 degrees. All right. What is this number? 0.45 meters. Oh, that's the length of the potato gun. So, gee whiz, from here to here is 0.45 meters. Wonder what this one's going to do. We want to find the potato's velocity when it pops out of the gun. Velocity equals question mark right there. Why don't we call that V0? That's at the beginning of the problem when it just pops out of the... won't draw it. When it just pops out of the barrel, I've got a V0, and they want to know what that is. They want to know the acceleration that's in the tube here. And then they also want to know the force. So we're interested in what's going on in the gun. And we know that it goes way up here to a maximum height. It's going to stop going up right there. It's going to keep moving to the right. But its y velocity is going to be 0 up there at the top. And we'd like to know something about what's going on down here. All right. Looks like there's some kinematics. V0, V. I got gravity pulling down for that part of the problem. A sub y equals negative 9.8 meters per second squared. It's down. We'll let the velocity and the distance be up. So that's why I put the negative on there. Okay. So we need to do some kinematics here. That'll help us get this initial velocity when it left the cannon and goes up there to stop. So this is a big problem. We're going to break the big problem into little pieces. And, you know, you may want to just come in here and say, well, here's V0. And it's going to go up, 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 up. And there's the final velocity up there. And, of course, we already put in the acceleration and stuff. But we should be able to find out something about this from what we've got. All right. I'm looking at V0, V, A, Y. There's no time involved, and I happen to have an equation that doesn't have time in it. So let's try that. V squared equals V0 squared plus 2AX. Normally we write, but here we're working in the Y direction. So I'm going to remind myself that this is the Y direction. I'm going to put some subscripts here and here. Instead of an X right there, I'm thinking about the Y distance. So let's try like that. It wouldn't hurt to come in here and put A sub Y, but I doubt it's going to let me get in there. So we'll just do that. I know the final velocity. I know the acceleration. I know the distance. That means I should be able to find V0. So let's subtract 2AY from both sides. That leaves me with V0y squared. And if I take the square root of both sides, then that will give me the speed that it pops out of the potato gun down there at the bottom. This V0 is 0. I'm sorry, the final velocity right here is 0. It stops up at the top. So what I need to do is take the square root of negative 2 times the acceleration, which was negative 9.8, times the maximum height, the 110 meters, like that. That'll find me the speed that it popped out at. Let's see here what we got. Square root negative 2 times negative 9.8 times 110 means that we're looking at 46.4 meters per second. So we'll put that in down here. All right, and that's the first question. That's kind of the first question. That's actually the y component of the first thing. So let me put equals v naught y right there, and v naught being the instant that it pops out of the barrel. All right. So we found the first thing. How fast is it going when it's shot out? All right. We'd like to know the acceleration, and here they mean the acceleration in the tube, I think. That's the problem I'm going to do. So here, find acceleration in the gun. And I think that's the right one they want. It's certainly slowing down from here to there, but when they ask for the force, I think they want the force in the gun. So I'm going to find the acceleration in the gun and see what happens. When I think about the barrel of the gun, whether it's pointed up at 80 degrees or whether it's level, doesn't really matter. Here is my potato gun. Here is the potato before I fire it. Here's when it pops out. And before I fire it, the velocity is 0. And when it pops out, we just found it's going 46.4 meters per second. Now, we just changed notation, didn't we? Here we called it v naught. That was the velocity when it began going up, and now I'm calling that v the final velocity when it pops out the barrel. So if you don't like that, you could come up with some other notation system, you know, and say, well, I'm going to call where is my, there it goes. You know, down here, I'm going to let this one be v naught, and this one could be v1, and up here could be v2. If you want to do something like that, knock yourself out. All right? That's fine. I've written it this way because this is a separate part of the problem. I took this big problem and I broke it into two little problems. Here's a little kinematics problem. Now I'm going to do another little kinematics problem. And my formulas are set up to say, well, at the beginning of this part of the problem, we're going to call it v naught, and at the end, we're going to call it v. But if you want to label that some other way, that's fine. I'm just going to do it this way. We're looking for the acceleration, and I know the distance here, the length of that tube is 0.45 meters. So that sets me up with that last equation, v squared equals v naught squared plus 2ax. And I'm looking for a, so I need to subtract v naught squared from both sides. That gives me 2ax. I need to divide by the 2 and the x. So v squared minus v naught squared over 2x equals a. And I have the numbers for that. I'll write them in here. I was trying to save a little bit of room, but I guess I need to put it. Here at the bottom, the final velocity was 46.4 meters per second. That has to get squared because the formula says so. And the v naught, that's a 0. I think it's squared, doesn't really matter. It's going to go away. Down here I've got 2 times the length of the tube is 0.45 meters. So I need to do that. We know, of course, to be very careful with this, I got to do 46.4 and square that, but then I want to divide by 2 and also divide by 0.45. So you could either say divided by 2 divided by 0.45, get that number. If you don't like that, you can say 46.4 divided by parenthesis 2 times 0.45. That'll work fine too. All right, either way works. So that's my acceleration. That's the second thing they wanted to know, and I didn't even look at the number. 2392. And that's going to be meter per second squared because it's an acceleration. Because up here I got meters squared over second squared, this cancels one of the meters, and I'm back down to that. So there's answer number 2. that they ask us for. And I think I've got just enough room here to squeeze in number 3. They say, go get me the force. And I get a big grin on my face because I know that's easy. F equals ma. I've got the mass is 0.5 kilograms. I've got the acceleration 2392 meter per second squared. And I'm looking at about divided by 2 here, or times 0.5, 1196 newtons. Okay, kilogram times a meter per second squared to be a newton. All right, so there's all 3 parts of that. I kind of told you this would be the first part of all of those, you know, the starting point of all these. This one had some extra stuff they wanted us to find. Sometimes you got to have the kinematics, and sometimes you got to have the Newton's law. We're learning all of these things, so keep them all together. The whole class is cumulative. People get excited and say, well, is the final cumulative? Well, yeah, test 2 is cumulative, and test 3 is cumulative. Keep all of the stuff that you're working with, and don't leave any of it behind. Here's an elevator. I'm going to draw an elevator. Okay. There's my elevator. It's full of people. Okay. You can put the people if you want. There is a mass of 1,700 kilograms, so I know that gravity is pulling down. And it accelerates upward. Why is it accelerating upward? Oh yeah, because there's a cable. There's some kind of mechanism that pulls this thing upward. I'm going to call it T for tension. They're looking for that. All right. But this acceleration is important. So I'd put that in my picture. Okay. You probably ought to get credit for taking this class. Probably ought to get a physics credit and an art credit because we draw so many pictures. But you see how simple the picture makes that? Cable pulls up, gravity pulls down, it's accelerating upward. Okay? As soon as you can see that, you say, well, gee, it's a force problem. I'm going to write down Newton's law. I see that there are 2 forces, and that's going to be equal to ma. They're asking me for the tension, so all I have to do is add mg to both sides, like that. And I know that the mass is 1,700 kilograms, and g is 9.8 meter per second squared, and the mass is 1,700 kilograms, and the acceleration is 1.2 meter per second squared. And I'm going to multiply this thing out, but I'm going to do it in pieces just to kind of make a point. In real life, I would probably just go ahead and do this whole thing. Well, let's get this number right here, 16,660. And then over here, I've got another 2,040 newtons. The reason I took this apart, or did it in pieces instead of just punching the whole thing up and getting a single number, is this is the weight of the elevator. The cable has to hold that much just to hold the thing up. And then this is the acceleration. If you want to accelerate it, you've got to pull harder on the string, right, to make it go faster and faster. If you wanted a bigger acceleration, then you'd have to pull harder. Okay? And the sum of those 2 numbers is the total thing here. Looks like that would be 18,700 newtons. Something like that for the tension in the cable. If there are some forces in the problem, you need to draw a box and some forces. And you need to come here to Newton's second law. Here's one right here. I think I got 2 more for you. A block on a frictionless table. There's a table, here's a block, and it says that's 4 kilograms. All right, got a block on a table. It's pulled to the right by a 1 kilogram hanging mass. A hanging mass, that would be over here. That's another mass, 1 kilogram. Maybe it would make sense to call this one mass 1. And the stupid thing ain't gonna let me do it. Sometimes it will if, oh, I lost my pencil. If I change color, sometimes it lets me sneak in there. Oh yeah, there we go. All right, mass 2 is 1 kilogram. All right, name these however you want, MA and MB or something like that. But keep them straight. All right, give them separate names if that helps you keep these things separate. Now there's a string here that this thing is hanging from. So I want to draw this string. And there's a whole class of these problems. It's kind of understood that there's a pulley here, or it's going off the edge of the table and it's perfectly smooth or something. There's lots of assumptions that we make to do these problems. I'll just put a couple of them here. The pulley, anytime you have a pulley in one of these problems, it has no mass. It's not an object of itself. And there's no friction. Okay. Now we can do problems where the pulley has mass and when it has friction, but we don't usually do them in first semester physics. All right. Those are a little more involved, and we kind of leave that out. So if I draw a pulley, and or just even let the string run off the edge of the table, it's kind of understood that there's no friction there. There's nothing in this. I'm interested in this box and that box and how they're going to move together, but we're not interested in the pulley in itself. All right. The second assumption I'd like you to always put down for me is that the string has no mass. And no stretch. Okay. If I put a 40-pound log chain in place of the string, that makes the problem a lot more tricky. Okay. I don't want the string to be an object in and of itself. I'm interested in this box and this box, and I don't want to think about the string or that connecting thing as a third object. All right, so anytime I draw a string, it's not going to have any mass. It's also not going to stretch. If I put a rubber band in between these two and turn loose of this guy, he's going to drop really fast, and then he's going to bounce back up, and it's going to kind of jerk this guy, you know, back and forth. And we don't want our strings to stretch. We want both of these boxes to move together smoothly in a nice orderly fashion. Then we can apply these formulas and see what's going to happen. Again, we know how to do the other problem with the rubber band between it. We know how to do the problem with the log chain in between it. But we don't do it in first semester physics. We do that in a class called mechanics or dynamics, something like that. All right. This one is a little bit different because we have two objects. So what I'm going to have to do here is to come in here and think about the forces on this mass and write the equation, the sum of the forces on mass 1 equal mass 1 times A. So I only want to think about the forces right here, and I can say, well, it's moving to the right because this string is pulling on it to the right. So that's a force that I need. They want me to find the tension in the rope. That's what this force is. So I'm going to call it T for tension. I start looking for other forces that I might need to put in my picture. I say, well, it's got mass, so, oh, don't do that. It's got mass, so I know it's got gravity on it, right? And I could come in here and draw the weight of that box, gravity pulling down. But I also know it's sitting on a table, and that table is pushing up. So right there's the normal force, and this is mg, and I already know those are going to cancel out. Okay? So maybe I don't even put them on my picture. If they don't do anything, what's the point, right? They told me that the table is frictionless. If I did have friction, it would slow me down. It would be a backward force. We're going to look at that eventually. But right now we don't have friction, so I don't need that one. The only force on that mass 1 is T. So when I make a list of the forces on mass 1, there's only one thing, only one guy there. T equals M1A. I don't know what T is. I do know that mass is 4. And I don't know what A is. So there's 2 unknowns here, and I can't solve this problem just yet. I have to leave this, and maybe we'll come back to it and see if we can't, see if we can't do something with it later on. But right now we're kind of in a jam. And I was trying to move all this up, but it doesn't want to cooperate with me, so we'll just leave it there. Okay, what are we going to do? Let's go look at the other box. That's about all we can do. Hopefully we can get an equation we can solve over there or something and bring it back. Looking for a color I haven't used yet. Let's try black. All right, this guy has mass, so gravity is going to pull down. M2G is what I would put on there. That's the weight of the box, the force of gravity pulling down. I also see this string right here, and that's going to be an upward force. Now, you say, why is it an upward force? And I say, because it's slowing that box down. The box wants to fall, but the string is keeping it from falling. Sometimes it's useful to think about giving things the scissor test. If I go in there and cut that piece of string, then the box is just going to go into free fall. All right? But as it is, the red string is slowing that down. It's keeping it from falling. So that's an upward force. And I need to draw that force in there. Okay. I don't have friction on this one. I don't have anything else. There's kind of a little list of possible forces I'd like you to kind of run through here every time we do one of these. Let's see where I can put this. The possible forces that tend to go in your picture would be gravity. Okay? If you're on Earth, gravity is pulling down. The only time you wouldn't need gravity is if the normal force is canceling that out. So that's another possible force. In this case, box sitting on the table, gravity pulls down, but the normal force cancels it out. So both of these go away. In this box, gravity pulls down, but there's nothing under it. There's no normal force to cancel it out. So I definitely need this guy, but not that one. All right? I do need the string, so I'll put tension in this list. Anytime there's a string in your problem, you need to put that down as one of your forces. It needs to go in your picture, and then it needs to go in your equation. All right? What else could we have? If you had friction, and again, we haven't really done that yet, but we kind of thought about it over here and said, no, we don't need that. That would be a possible force we could put in our picture. And we're going to eventually have something called a downhill pull. That's kind of my name for it. Anytime you put something on a hill, gravity tries to slide that downhill, and we'll see that always should be mg sine theta. Again, we're kind of getting ahead of ourselves here. But that downhill pull is a possibility. And other than that, the only other thing I can really think of is some kind of external force. Maybe there's a guy pulling on it. Maybe the wind is blowing. Maybe a car engine is pushing a car forward. Some kind of other force. So external, other, something like that. And you're kind of, going through that list and saying, do I need gravity in this one? Is there a string? Is there friction involved? Here it said it's frictionless, so I didn't. Okay? But there's a list of usual suspects here, and we kind of want to exhaust that list and make sure we've got everything. Now that I've exhausted you and you've exhausted me, we can look at this box right here and say this is the sum of the forces on mass 2, and that's equal to mass 2 times A. And I look and I say I've got two forces. There's T, there's M2G, so I'm going to put those down. Okay? But there's a trick right here. There's a gotcha. And you got to be careful with this. So let me come in here and draw something for you. This box, the one on the table, is going to move to the right. So the positive direction is to the right. I like to call the direction of motion positive. And if you look down here, T pointed to the right in the direction of motion, and we said that was positive. Okay? If we had had friction, that would have been to the left. That would have been opposite. It would have been negative. Okay? Direction of motion says positive. That's great. We got this one right. I need to figure out the signs for this guy. So when I think about the direction of motion of this box, direction of motion is down, which means I need to call the coordinate system down positive. There's two ways to think about this. One, you can say, I always want the direction of motion to be positive for all the boxes. Okay? For this guy, direction of motion is positive to the right. For this guy, the direction of motion is positive down. That'll work every time. If you don't like that, what you can say is, I need one coordinate system for the whole problem, and that coordinate system is going to follow the string. So here our coordinate system is moving to the right, and when the string bends over that pulley, then the coordinate system bends right there too and goes down. Either way works fine. But if you want to get this problem right, then you need a minus t and a plus m2g. The direction of motion positive down, m2g is down, so he gets a plus sign. The tension is fighting that, is backwards. It's slowing it down, it's taking away, it's subtracting, it's negative. All right? That's the trick right there. If you can get those signs right, then you'll be fine. All right, let's see what we know about this thing. I'm going to go back to black because I think it's a little bit easier to see. But I don't know what T is, so I got negative T. Plus M2, oh yeah, that's 1 kilogram. G is 9.8 meter per second squared. M2, that's 1 kilogram. A, I don't know what A is. Now, I like to simplify these just as much as possible, so I'd have negative T. 1 times 9.8 is 9.8. I already know that's a force. It's in newtons. Looks like that. Here's a 1 times A. I'll leave the 1 in. In practice, I'd probably leave the 1 off, but same thing here. Okay, that's my equation, and I can't solve that one either. Cooked up 2 equations. Here's the first one. It's got 2 unknowns. T and A. Can't do anything with it. Here's the second one. T and A. Two unknowns. I can't do anything with it. All right. So I've got a system of equations here, simultaneous equations, and I need to solve for T and for A. You've got 2, 3, 4 choices, 5 choices. Substitution method works. The matrix thing works, but good gracious, that's a whole lot more power than you need for a little simple problem like this. The easiest, best thing to do is to stack these up. Here's T equals 4A right there. If you just stack the first and second equation and draw a line underneath and add straight down negative T, and T is just going to cancel out and give you 0. 9.8 plus 0 looks like that. 1A and 5A, I'm sorry, 1A and 4A would be 5A. So if I divide by 5, I'm going to get 1.96, a little bit less than 2 there. And that's going to be the acceleration of this system. Okay? We have one of our answers now. We didn't know either one, but now I've got A. I could take this number and plug it in up here and find T, or I could take A and plug it in over here. Multiply by 4 and get T. That sounds a little bit easier. So I'm going to say T is equal to 4 times 1.96, and that's going to be 7 point something, a little bit less than 8. 4 times 1.96 is 7.84. And now I've got my tension. All right. So that's what you want to do there. This one has two masses. I got to build an equation for the first mass. I got to build an equation for the second mass. I'm always going to sum of the forces equals mass times acceleration to do that. And in order to add the forces, I have to know what the forces are. So I draw a free body diagram and with all its forces, and I draw a second free body diagram with all its forces. Use the first picture for the first equation, second picture for the second equation. Got to get my signs right. The signs have to match up. Let me say it like this. Those two boxes are physically tied together with a piece of string. They need to mathematically be tied together with a coordinate system. All right. So that would be the way of that. All right. One more problem. And well, I thought I had one more. What's going on? Won't give it to me. There it is. Okay. String over a pulley holds a 4 kilogram mass and a 5 kilogram mass. I got to have a picture. I got to know what's going on. Here's the pulley. There's the 4 kilograms. Hanging straight down is the 5 kilograms. This one did not say anything about a table or anything like that. It's just two masses on a string over a pulley. And so we've got that. I need to think about the forces that are acting on this thing. Of course, gravity's doing its thing. Tried to change that to a red. I don't know why it didn't come out red. Still not red. Be red. Thank you. Gravity pulls down. The way that I get gravity is to say mg, the mass of the object times its acceleration due to gravity. So right here I'm going to put m1g. Let's call this one mass 1 and this one mass 2 again. All right? Gravity pulls down. That box is going to go up. And I know it goes up because it has less mass than the other one. This one's heavier, so gravity's pulling down more. That's going to pull the string on the right down, pull the string on the left up. It's going to lift that box. So let's call this T. That's what I need to know there. There's no guy pushing on it. There's no friction. There's no wind. Those are the two forces that I need. If we look back at that list of possible forces, this is what we've got to work with. So I'd write the sum of the forces on the first mass equal to mass 1 times A. Now, the notation's not meant to be tricky. It's meant to help you get through this. If you want to come in here and say 4 mass 1, right, or whatever it takes, but that's what we're trying to do. Write down Newton's second law for this box right here. 1, 2 forces. So I got to go T and M1G equals M1A. The tension is up, as is the direction of motion. So up is positive, T gets a positive. M1G is in the opposite direction, it gets the opposite sign. I don't know T. It's a 4 kilogram mass. So I'd end up with this equation. All I can do is simplify 4 times 9.8. That'd be 36 plus 3.2 would be 39.2 equals 4a. You notice I left the units out there. I try to get this as simple and as clean as possible. As soon as I see that everything's in kilograms and meters per second squared, I'm confident that the units are going to behave themselves, and I just do like that. All right. Probably be better to write them in, but it just gets messy. Okay. Right here, I'm going to write the sum of the forces on mass 2 equal to mass 2. Because I can't solve this, I don't know T, I don't know A, I need a second equation. If you have two unknowns, you got to have two equations. Think about the forces acting on mass 2. Gravity pulls down, and the string once again pulls up. This is exactly the same picture, and therefore exactly the same formula that we ended up with last time. It's going to look like that. the direction of motion is down. So down is positive. This guy gets a plus sign, this guy gets a negative sign. And that's going to look like this in my equation. I fill in what I know. That mass was 5 kilograms times 9.8. And that's equal to 5 times A. I don't know A. All right. But here I'm going to have 45 and 449 equals 5A. And that's as good as it's going to get. I don't know T, I don't know A, I can't solve this one, I can't solve that one. It's time to do that stack and add thing that we did before. Let me pull them down here and do it separately. Maybe this is easier to see what's happening. But here's the first equation. Right below it I'm going to write the second equation. The T minus T cancels. Negative 39.2 plus 49, that's going to be a positive 9.8 equals 4A plus 5A is 9A. And when I divide by 9, my acceleration is going to be a little bit less than 1.1. 9.8 divided by 9 is 1.0809, something like that. Meter per second squared. Tack your units back on right there. All right. If you don't like this stack and add thing, and I don't know why you wouldn't, because this is the easiest way to do it, you are welcome to do substitution method, or matrix method, or Kramer's rule, or row operations, or graphical solution, or anything else you want to try. But stacking up and add always works, because you're always going to have a plus T and a minus T. If your T's don't cancel out, you set your coordinate system up wrong, and you need to go back and do it again. All right? The T's have always got to cancel out, so that's a little safety check to make sure you did the coordinate system right. I could take A and put it right there, solve for T, but you know what? I don't like that negative sign sitting right there. So I'm going to go the other route with it. I'm going to take A and plug it in up here, solve for T. I'll get exactly the same number, exactly the same answer. So if you want to go over here, that's fine. I just don't like dealing with the negative signs. So if I add 39.2 to both sides, and I've got that 4 times A being 1.09, I can find that tension in the cord. The tension is important because at some point you're going to have to build something. Everything that gets built, somebody has to go through and design the thing mathematically and make sure it's going to stand up. Your house, your car, they had to know what forces were going to act on it and account for that. 43.6, I'm going to call it, okay? And make sure that they had enough steel or enough wood or whatever it was to do this. If I have a string that only holds 40 newtons and try to make this elevator system right here, I'm going to break the string, and all the little people, all the screaming people in the car are going to fall and die. All right, so finding that force is an important thing. Somebody's got to do it. You could be that person now because you know how to do these problems. Draw the picture. If you got 2 boxes, you got 2 boxes. That means you're going to have 2 equations. If you had 16 boxes, you'd have 16 equations. All right, set up a coordinate system. Get all your forces. Solve whatever that takes. All right. Sorry that took so long, but hopefully that'll work out. I've got lots more examples coming for you. Please, any questions you have, bring them to class and work as many of these as you can. You'll see some patterns that these things fall into, and it'll be all right. Thanks.